So far, we've been talking about the interpolating polynomial as though nothing could ever go wrong with it. And in point of fact, for many purposes that we're going to use it for, nothing can go wrong. But there is such a thing as sampling error, which I'd like to talk about today. I want to think about what would happen if we had some bad data. What if our data points were 1, 0, 2, 0, 3, 0, and 4, 0, which would be these dots on a graph. All of the numbers in my interpolation table in column 0 would be 0. And since I take differences of those, all of the divided differences will be 0, meaning that my interpolating polynomial will be 0 times x squared plus 0 times x plus 0, for instance. It's the polynomial that's 0 everywhere. Unfortunately, my actual function, unbeknownst to me, might be f of x equals 5,000 times sine of pi x, which is 0 at x equal 1, 2, 3, 4, and so on. However, the graph of 5,000 sine pi x doesn't look anything like the graph of y always equal to 0. So our interpolating polynomial would not look very much like the actual function if that were important to us. So we're going to introduce a new idea. We're going to look at Hermite polynomial interpolation. We're going to build in information not only about the x coordinates and the function values, but other pieces of information as well. And a key fact that we're going to rely on is the definition of the derivative of a function back from Calculus 1. So we're going to play a game of make-believe. We have x0 through xn and f of x0 through f of xn. I'm going to pretend that I have twice as many data points as I actually have. I'm going to pick some positive number epsilon, which is smaller than the smallest distance between any two different of my x values. If I increase my given x values by this small amount epsilon, I still maintain a distinct set of x values, although I have twice as many as I did before. The indexing on the original data x's was 0 to n. We had n plus 1 data points. If we double that, the number of data points will be 2n plus 2. And since our index begins at 0, the indexes on our new set will go from 0 up to 2 times n plus 1. And I'll probably end up calling that number m when I write my program. Even without doing anything yet, I already know what the error is going to be. I'm basically just doing an interpolating polynomial when epsilon is positive. The number of data points is now 2n plus 2 instead of n plus 1 as it used to be. Our previous work tells us the difference between the actual function value at some number z and the value of what I'll call h for Hermite polynomial at z is going to be some value of the 2n plus second derivative divided by 2n plus 2 factorial times the product of z minus each of the relevant z numbers in my data set. So for example, if I had originally 3 x values with index 0, 1 to 2, I'm now going to have 6 z values to correspond with them. The indexes will go from 0 to 5. z0 will just be x0, z1 will be x0 plus epsilon, z2 will be x1, z3 will be x1 plus epsilon, z4 will be x2, and z5 will be x2 plus epsilon. For each one of these z values, there is a corresponding function value to go with it, which you'll recall are polynomials of degree 0, which interpolate at single individual z values now. Since all of my z values are distinct, there is nothing stopping me from carrying out the Newton interpolation table, the divided difference calculation. I will combine these two pieces of information to get that one, these two pieces of information to get that one, and so on down the list. When I've got all of these pieces of information, I'll combine this one and this one to get that one, this one and this one to get that one, and it's exactly the same formulation that we had before, except the indexing is twice as big as it used to be. Now, I'm going to make trouble for myself. If the epsilon were 0, because I have repeated function values and repeated x values, for some of them, trying to do the standard Newton divided difference formula would cause division by 0, and of course we can't have that. On the other hand, if I don't set epsilon to 0, but I think of it as just being very small, maybe less than 10 to the minus 7, or 10 to the minus 15, or 10 to the minus 500, or take the limit as epsilon goes to 0, then philosophically there's no trouble. I'll have f evaluated at some xj number plus epsilon minus f evaluated at the xj divided by xj plus epsilon minus fj. The bottom of the fraction is going to be epsilon. Now, mathematically speaking, if epsilon is small but not 0, there is absolutely no problem with this. Of course, I wouldn't actually want to put that expression in my computer because of the subtract two nearly equal numbers thing. If epsilon is small enough, the top of the fraction will evaluate to 0 even when it shouldn't. This difficulty occurs only in column k equal 1. For columns k equal 2 and later, the indexes on the z numbers differ by more than 1. So even if epsilon had been set equal to 0, I'm never going to get division by 0 in that case. So it seems as though column k equal 1 is the only thing I really have to worry about that's different from the standard Newton divided difference form. So I'm not going to calculate that difference quotient in the computer because I know it wouldn't go well. I'm not going to set epsilon equal to 0 in the computer because that wouldn't go well. We're not going to do this in the computer. We're going to do it in our brains. So what we'll end up doing is taking the limit of every number in that table as epsilon tends to 0. So having said that, I now have a piece of paper with the table on it that says, take the limit as epsilon goes to 0. We have to see how to do that. Now, the column of z values, it's obvious, all of the z numbers were one of the x numbers plus epsilon. As epsilon tends to 0, the z numbers all tend to x numbers. Some of them actually were x numbers already. Others were x numbers plus epsilon, so the limit is x numbers again. In my Hermite table that I'm building up, the independent variable column is going to have z0, z1, z2, z3, z4, and z5. But secretly, now that we've taken the limit, the x numbers show up twice in the table. There's x0, x0, x1, x1, x2, and x2. Since we're assuming that our function f is at least continuous, when I take the limit of f of x something plus epsilon, as epsilon tends to 0, I just get back f of x0, f of x0, and so on and so forth. After column k equal 1, everything's done as usual. So we have to worry about what to do with these quantities, which is what we're going to talk about next. So I'm actually going to sit down and write these limits out. The first number in column k equal 1, that'll be the one that has row index I equal to 1, is going to be the limit as epsilon tends to 0 of f of z1 minus f of z0 over z1 minus z0. If you put in what z0 and z1 are, that turns into this limit. In the denominator, the x0 cancels out, and I'm just left with this, which if you think of x0 as being the point you're interested in, and the epsilon as being delta x, this is just the definition of the derivative of f at x0. So the top number that I put in column 1 should be a value of the derivative. The next one down after that, we've got to take the limit again, but this time my divided difference is based on z1 and z2. So putting in what z1 and z2 are, f at x1 minus f of x0 plus epsilon. On the bottom, x1 minus x0 plus epsilon. As epsilon tends to 0, the denominator tends to x1 minus x0, which is not 0 because in the original data set, I had distinct x values. Meanwhile, since our function is assumed to be continuous, the limit as epsilon tends to 0 of x0 plus epsilon is just f at x0. Again, going back and looking at the table after we have done the limit, that would just be this expression. So if I was going to get division by 0 in this limit table, I've got to put in a derivative value instead. On the other hand, if I don't get division by 0, I'm just going to do the usual Newton formula, except it's z numbers and f of z numbers now. In case you're not convinced, do the next one. I want to look at the limit of f bracket z2, z3 before I've let the epsilon go to 0, and then I want to see what happens when I take that limit, write in what z2 and z3 are. The same thing happens to you. On the bottom of the fraction, x1 plus epsilon minus x1 is epsilon, and this limit is the definition of the derivative of f evaluated at x1. So we should see what the plan's going to be now. To gain the effect of doubling the number of points and then taking the limit as the changes in the x coordinates tends to 0, we will have the following plan. In my independent variable column, I'll have z0, z1, and so on, but these are actually repeated x values. I'll have the corresponding function values in column k equals 0 of my table. When I go to construct column k equal 1, I'm going to have an alternating back and forth behavior. At the beginning, I use a derivative value. In the next one, I use the ordinary regular old Newton divided difference formula. Then I do a derivative value. Then I do the ordinary formula. Then I do my last derivative value. This is how I'm going to establish column k equal 1 of my Hermite table. After that, though, for k2 out to however many columns you have, you're always going to use the R formula, which in the case of column k equal 1 is this formula. An observant person will notice that you're going to use derivative values when the row index I is odd, and you're going to use the usual formula when it's even. So obviously, I'll make the distinction using the mod function here. Of course, we have to actually set up the column that represents the independent variable and the corresponding function values. So I've got to decide what goes where. If you look in the table, x0 gets stored into z0 and z1. x1 gets stored into z2 and z3. x2 gets stored into z4 and z5, and it should be pretty clear what's going on here. If you double 0, you get 0. 2 times 1 is 2. 2 times 2 is 4. So x number I is going to be stored into z number 2 times I. But not only that, x number I is stored into the next one after that in the z array as well. X number I is going to get stored into z number 2i and z number 2i plus 1. Since the indexing on the function values is the same as that for the z values, function value number I will get stored into function value number 2i and function value number 2i plus 1. Now, of course, later when we put our table in our program, we'll have a two-dimensional array, and we will have to store the appropriate numbers in the appropriate places. So this is going to be column k equals 0 in my t table. This will be column k equal 1. That's the only one that requires special treatment. After that, it's business as usual. So in an attempt to get better polynomials, I'm going to assume that not only do I know the x values, the corresponding function values, but I also know the values of f prime at x0 through xn. To initialize my data, I'll do this loop. The reason that I'm doing the loop over indexes on the x variable instead of the z variable is that we have figured out where x number I goes into the z array. So it seems like a natural way to do this. You could do the calculation based on the indexes of the z values, but I believe that would be more complicated and more trouble than it's worth. How do we deal with the k equal 1 case? We figured out which row in my table f prime at xi is going to go into. When I is 0, 2 times I plus 1 is 1. So f prime at x0 is going to get stored into t1, 1. When I is 2, when I is 1, that is, f prime at xi is going to get stored into 2 times 1 plus 1 is 3, comma 1, which is the correct row. At the very end, when I is equal to n, the value of the derivative that goes with x number I is going to get stored into row number 2 times n plus 1, which, if you'll remember, is the largest index in the t table. So this is going to put the derivative values into the appropriate slots in column k equal 1. Now, if you'll remember, our pattern has always been when we put a number in the table, it's the difference of the number immediately to the left and the one above that, divided by 2 consecutive differences of the independent variable values. So if I want to look at t number 2i, which is going to be something in column k1 with an even index, I move backwards 1 column and look at t same row, comma 0. The one above that, minus 0. And on the bottom, I have to take the difference of 2 z values, the z value with the bigger index minus the z value with the smaller index. So I'm just doing the usual divided difference formula here. What about the rest? There's no problem with the rest. We have figured out how to do this previously with the Newton form. Once we get past column k equal 1, everything works exactly as it did with the Newton form. So I'll look at columns do k equals 2, because we already did 1, out to not n, but m, because we're doing the Hermite form. Do I equals k to m. This formula, except for the fact I'm calling my array that holds my independent variable values z instead of x now, this is exactly the same as the Newton divided difference form. Coming up next, how will we actually write programs to do this? Also, how will we evaluate the Hermite polynomial? Will we need a new function like our p function that we've used previously for the Newton form, or can we just reuse it somehow? We'll see that when we talk about it during the next discussion. In the meantime, I hope all of you are having a good day, and I'll talk to you again real soon.